Hi everyone, this is NLP Corgi. Today's deep dive is about the paper from Google Foundational Large Language Models and Text Generation. This presentation walks through how large language models evolved from the original transformer into today's powerful systems. We'll look at how model size, data, and architecture changed over time, what that means for performance and efficiency, and how modern models are trained, fine-tuned, and deployed. The goal is to give you a clear mental map of the LLM landscape, not just a list of model names. Everything in this story starts with the transformer. Instead of processing text step by step like an RNN, transformers use attention to look at all tokens at once and decide what matters. Inputs are embedded into vectors, passed through stacked layers of multi-head self-attention and feed-forward networks, and stabilized with residual connections and layer normalization. This simple but powerful blueprint underlies almost every modern large language model. Self-attention lets each token decide which other tokens are relevant. We project the sequence into queries, keys, and values, compute similarity scores, and use them to form weighted combinations of the values. Multi-head attention repeats this process in parallel with different learned projections. Each head can specialize in different patterns, like syntax, long-range dependencies, or entity tracking, and their outputs are combined to form a richer representation. As models grew, simply making every layer dense became too expensive. Mixture of Experts offers a clever alternative. Instead of one big feed-forward block, you have many expert blocks, and a small router chooses just a few to run for each token. That means the total parameter count can be huge, but the compute per token stays manageable. This sparse activation is now a key ingredient in several frontier models. For a while, the field assumed that simply increasing parameter count was the main path to better models. Kaplan and colleagues quantified how loss improves as you scale model size, data, and compute, and recommended scaling parameters faster than data. The Chinchilla paper revisited this and found something striking. For a fixed compute budget, the optimal strategy is to scale data and parameters roughly equally. That means many large models were actually too big for the amount of data they saw, and could have been smaller, but better trained. When you look closely at how performance changes with model size, you see a nuanced picture. Bigger models tend to show strong improvements on tasks like logical reasoning and reading comprehension. But for broad general knowledge, performance can plateau, even as parameters keep increasing. This tells us that simply scaling size is not a universal solution. The type of task matters, and so do data quality and training strategy. The first wave of large language models like GPT-1, BERT, and GPT-2 showed that transformers could handle a wide range of language tasks with simple pre-training objectives. GPT-3 then dramatically increased scale, demonstrating impressive few-shot and zero-shot abilities. After that, the focus shifted from just getting bigger to getting smarter and more efficient. Better data, better training recipes, and more specialized architectures. DeepMind's Gopher showed what a 280 billion parameter dense model could do across knowledge and reasoning tasks. Guam took a different route. It used a sparse mixture of experts design with 1.2 trillion parameters in total, but only a fraction of them active for each token. That allowed it to outperform GPT-3 while using about a third of the training energy and half the inference flops, highlighting the power of sparsity at scale. To test the new scaling laws, DeepMind trained Chinchilla, a 70 billion parameter model, using the same compute budget previously used for the much larger Gopher. By reallocating compute toward more training tokens instead of more parameters, Chinchilla consistently beat Gopher, GPT-3, and Megatron Turing NLG on a wide range of benchmarks. It was not only better, but also cheaper to run and easier to deploy, which strongly influenced how later LLMs were designed. Google's Palm series pushed scale and engineering. The original Palm, with 540 billion parameters, was trained on a massive mix of text and code and achieved state-of-the-art results on benchmarks like Glue and Superglue, as well as challenging reasoning and coding tasks. Palm 2 refined the architecture and training recipe, delivering better performance with fewer parameters. This showed that smarter design can sometimes beat raw size. The Gemini family moves beyond text-only models. Gemini can take mixed sequences of text, images, audio, and video, tokenize them, and process everything through a unified transformer decoder. Under the hood, it uses mixture of experts layers and efficient attention variants like multi-query attention, and it's tightly optimized for Google's TPU hardware. This design lets Gemini handle very long contexts and complex multimodal reasoning tasks. Gemini 1.5 Pro dramatically extends context length into the millions of tokens and still maintains high recall even on documents with up to 10 million tokens. It can reason over long code bases, multiple long documents, and hours of video. The Gemini 2.0 generation introduces specialized variants: Flash for fast, cost-efficient workloads, Pro as a general workhorse, Nano for on-device use, and Flash Thinking as an experimental model that emphasizes explicit reasoning and explainability. Gemma brings many of the ideas behind Gemini into the open model ecosystem. The first Gemma models use a large vocabulary and multi-trillion token training to deliver strong performance in relatively small packages, including a 2 billion parameter model that can run on a single GPU. Gemma 2 pushes a 27 billion parameter model to performance comparable to much larger systems like Llama 3 70B. And Gemma 3 adds multimodality and long context windows, making these models practical and accessible for a wide range of developers. Meta's Llama models helped catalyze the open LLM ecosystem, offering strong decoder-only models in multiple sizes, with chat-tuned versions like Llama 2 Chat and later Llama 3.x variants. Mistral's Mixtral 8x7b uses a sparse mixture of experts design to deliver performance similar to much larger dense models while keeping inference efficient. Around them, a growing set of open families, such as Qwen, Yi, and Grok, are rapidly improving, giving researchers and builders a rich menu of models to choose from. A newer trend is models explicitly optimized for reasoning. OpenAI's O1 series uses reinforcement learning to encourage long, deliberate chains of thought before answering, which pays off on hard coding and science problems. DeepSeek shows that similar reasoning performance can be reached with a different RL recipe, called Group Relative Policy Optimization, and a multi-stage pipeline that mixes supervised fine-tuning, pure RL, rejection sampling, and final polishing. These models highlight that training strategy can be as important as architecture. If you compare early transformer models to modern LLMs, the scale difference is dramatic. Parameter counts went from a few 100 million to hundreds of billions. Context windows expanded from a few hundred tokens to thousands, and now into the millions for some models. Training data grew from roughly 100 million tokens to well over 1 trillion. These shifts in hyperparameters underpin the emergent abilities we now see, like few-shot learning and complex reasoning. All large language models start with pre-training. The model is shown massive amounts of text, and often code and other modalities, and simply asked to predict the next token. This deceptively simple objective forces it to learn grammar, facts, and patterns of reasoning. Pre-training is by far the most resource-intensive phase, often taking weeks or months on large accelerator clusters, but it creates a general-purpose base model that can be adapted to many downstream tasks. Once a base model is pre-trained, it's usually not yet a good assistant. Supervised fine-tuning addresses this by training on high-quality, labeled examples, instructions, and ideal responses, question-answer pairs, dialogues, translations, and more. This stage teaches the model to follow instructions, hold conversations, and behave more safely. It uses far less data and compute than pre-training, but for very large models, it can still be a substantial effort. Supervised fine-tuning only shows the model positive examples. Reinforcement learning from human feedback, or RLHF, goes further by explicitly modeling what people prefer. First, a reward model is trained on human judgments comparing pairs of model outputs. Then, a policy gradient algorithm fine-tunes the LLM to produce responses that score higher under this reward model. This makes it easier to discourage unsafe or unhelpful outputs. Variants like RLAIF replace human raters with strong AI judges, and methods like direct preference optimization can skip the RL step entirely. Full fine-tuning of a multi-billion parameter model is expensive and often unnecessary. Parameter-efficient fine-tuning techniques solve this by training only a small number of additional parameters. Adapter methods insert tiny bottleneck layers into the model and train just those. LoRa freezes the original weights and learns low-rank update matrices instead. SONT prompting learns a handful of virtual tokens that condition the model without changing its core weights. These methods dramatically cut memory and compute costs while preserving most of the performance gains. In practice, you don't have to implement these fine-tuning techniques from scratch. On platforms like Google Cloud's Vertex AI, You can start from a base model such as Gemini 1.5 Pro, point to a training dataset, and launch a supervised fine-tuning or PEFT job with a few lines of code. The platform handles the infrastructure, training and deployment, and you get back an endpoint you can call like any other generative model. Even with the same model, the quality of your prompts can make or break performance. Good prompt engineering means stating the task clearly, specifying constraints, and often providing one or more examples. You can use formatting, bullet points, or explicit keywords to highlight what matters. For many applications, careful prompt design is the fastest and cheapest way to get better results without any fine-tuning. Once the model has a probability distribution over the next token, you still have to decide how to sample from it. Temperature controls how sharp or flat that distribution is. Top K and top P sampling restrict choices to the most likely tokens or the smallest set that covers a target probability mass. For tasks like coding or math, you might want low temperature and more deterministic decoding. For creative writing, higher temperature and broader sampling can produce more diverse and interesting outputs. To understand how well a model really works, you need systematic evaluation. That includes standard benchmarks for reasoning, coding, and comprehension, as well as safety and alignment tests. It's important to look at performance in zero-shot and few-shot prompting, not just after fine-tuning. And for subtle qualities like helpfulness, politeness, or bias, human evaluation is still essential, often combined with automated metrics. Serving large models efficiently is its own engineering challenge. Techniques like key-value caching let you reuse attention computations from previous tokens, which is especially important in chat settings. Speculative decoding pairs a small, fast model with a large one. The small model proposes several tokens, and the large model quickly verifies or corrects them. Combined with quantization, batching, and hardware-specific optimizations, these methods significantly cut latency and cost. In real-world systems, you rarely optimize for quality alone. Larger models tend to give better answers, but they're slower and more expensive to run. Smaller or distilled models are faster and cheaper, but may miss edge cases or subtle reasoning. Many applications use a tiered approach, a fast, lightweight model for most requests, and a larger model for complex or high-stakes queries. The key is to align your model choice with your product's latency, cost, and reliability requirements. The pace of progress in large language models is still accelerating. We're seeing models that natively handle multiple modalities, reason over millions of tokens, and tackle increasingly complex tasks. Both open and proprietary models are improving, giving users more options than ever. At the same time, questions of safety, alignment, data quality, and energy use are front and center. Understanding the foundations, architecture, scaling, training, and deployment puts you in a strong position to navigate and contribute to what comes next.